our previous lecture, we introduced the concept of input to state stability, ISS in short, which was for a given system that if you can find class K function beta and a class K function gamma, such that the solution, the normal solution, is always upper bounded by this term, okay, which represents the contribution of the initial condition, plus this term which represents the contribution of the disturbance. Okay, so since as time goes on, this becomes smaller and smaller. This inequality tells us that eventually this term will disappear, and if the norm of the input is, or the norm of the input is small in some sense, then the norm of the solution will remain small, at least eventually. Okay, an implication of ISS property was that if you set the input to 0, okay, or if you consider the disturbance-free case, okay, x equals f of tx 0, then the origin of that system, which we can call the input-free system, or the nominal system, or the disturbance-free system, is globally uniformly asymptotically stable, because in that case this term disappears, and what we have is norm of x is upper bounded by this class KL function, and which is the definition of global uniform asymptotic stability. Also, we established in the previous lecture that if, suppose that input is not 0 at all times, but it's converging to 0 eventually, in that case we show that the origin is attractive, that is, the state of the system must converge to 0. Okay. Now, in this lecture, we will talk about the Lyapunov characterization of input to state stability. Okay, so that's theorem 4.19 from the text. Let function, okay, 0, infinity, Rn to R, where n is the order of the system, be a continuously differentiable function such that its upper and lower bounded by the norm of the state pass through two class K infinity functions. Okay. Tx alpha 2 alpha x. Okay, alpha 1 and alpha 2 are class K infinity functions, and b dot, which is partial free with respect to t, plus partial free with respect to x, not that this is a row vector, multiplied by the right hand side, okay, less than or equal to minus w3 of x, provided that input is small in some sense compared to the norm of the state. Okay, rho of norm of m. Okay. For all txu triple in 0 infinity times Rn times Rn, and n is the size of our input vector, where alpha 1 and alpha 2 are class K infinity functions, that is, they are 0 at 0 continuous and strictly increasing and unbounded. Rho is a class K function, rho where we use to relate the norm of the state to norm of the input, and W3 is a positive definite function. Therefore, minus W3 is negative definite. Is a positive definite function. Okay, if such conditions are satisfied, then system is input state stable. Okay. Now let's apply this theorem or use this theorem to establish the input state stability of a simple system, so that we gain some familiarity with this new tool, theorem 4.19. Okay. This is an example from the book, example 4.27. Okay. Now consider the second order system. X1 dot equals minus x1 plus x2 squared, and x2 dot equals minus x2 plus u, where u represents the unwanted disturbance in our system. Establish for this system input to state stability using our new theorem, and we're also given a candidate Lyapunov function v for the example by the Lyapunov function candidate v of x as 1/2 x1 squared plus 1/4 x2 to the fourth. Okay, here is the solution. Okay, first of all, it's clear that V is positive definite with respect to the state of the system. Okay, x or x1, x2 considered as a state, and also it's radially unbounding. Okay, so note that this candidate is positive, definite, and readily unbounded. And readily unbounded means that as norm of x becomes larger and larger, v of x must also become larger and larger. Therefore, it turns out that we can always find for a function satisfying those properties two class K infinity functions, alpha 1, alpha 2, and this condition is guaranteed. Note that in our example, our system is not time variable, okay, so we're considering a special case. Therefore, level 4.3 from the text, there should exist two class K infinity functions. Let's call them alpha 1 and alpha 2. Satisfying alpha 1 norm of x less equal to v of x less equal to alpha 2 norm of x. Okay, so the Lyapunov function is sandwiched between two class K infinity bounds for all x in R2. So let's call this property 1. Note that the first condition in the theorem is satisfied. Now we also have to establish the second one, that is, we have to establish that v dot is less than equal to some negative definite function of x, provided that norm of x is sufficiently larger than the norm of the disturbance. Okay. So for that we have to consider v dot. Let's do that. so moreover, v dot, that is the derivative, time derivative of this function v along the solutions of the system is, okay, so v is here, our candidate. This dot is, okay, this dot plus that dot, and it's x, this is x, this yields x1 times x1 dot, and this yields x2 to the cube times x2 dot. Okay, so x1 dot plus partial of the second term with respect to x2 times x2 dot, and partial with respect to x2 yields x2 cube, and then we multiply that x2 dot. The dots x1 dot and x2 dot, they come from the system description, they come from the right hand side. So let's write them down. Minus x1 squared plus x1 x2 squared minus x2 to the 4 plus x2 cube times u. Okay, so this is v dot, and somehow we have to show that this is upper bounded by a negative definite function of x, provided that norm of x is larger than, in some sense, okay, norm of u, and in some we establish that in some sense-ness through a class k function. So we have to find a rho class k function. Okay, so let's play with the terms a little bit so that certain things become hopefully easier to see. So these are the nice guys, okay? Together they make clearly a negative definite whole. And then we want to use some of that negative definiteness to remove the effect of, or to bound the effect of, harmful effect of the input. So let's see how we can do that. So let's divide this, the sum of these nice terms into half, and what we have is 1/2 x1 squared plus x2 to the 4, and then another minus 1/2 times x1 squared plus x2 to the 4. And within that the other half, we also incorporate this indefinite term, okay, x1 times x2 squared. It could be either positive or negative, so potentially it's harmful. So we have to take care of this. So let's do that by writing, okay, x1 squared, the other half coming from here, minus 2x1 x2 to the 2 plus x2 to the 4. Okay. Now that this plus that gives us these terms. Okay, it's just a rewriting of the first three terms plus the input term x2 cube u. Okay. Now, one nice thing about this term is it can be written as a complete square. Let's do that. Minus 1/2 x1 squared plus x2 to the 4 minus 1/2 x1 minus x2 squared squared. Okay. Plus x2 cube u. Note that here we have something squared, therefore this is always positive, and it's multiplied by minus 1/2, therefore this term is always negative. So it's a harmless term, and we can just ignore it because it's not necessarily positive definite, and we can therefore upper bound this whole chunk by minus 1/2 x1 squared plus x2 to the 4. We can remove that, okay, because it's never positive, plus, right, x2 cube u. And then take 1/2 of this term to deal with the input term. So that's less or equal to minus 1/4 x2 x1 squared plus x2 to the 4 minus 1/4 x1 squared plus x2 to the 4 minus x2 norm cube times the absolute value of u, or norm of u. Okay, now let's call this as our minus w3 of x. Okay, so this is therefore w3, and this is minus w3 of x. And let's call this term, okay, let's call this term as g of xg. Okay, so what we have therefore, what we have achieved is v dot is less than or equal to minus w3 of x, okay, negative definite term, minus another term that contains the effect of the input. Okay, we're calling that term g of x of u, g of x u. So therefore, let's write it. This equals minus w3 of x minus g of xu. Okay. Now, if we can show that, provided that norm of x is larger than some function of norm of u, then this term g is positive. Therefore, this term minus g is negative. Then we would have obtained the condition in the previous theorem. Okay. Now here is the claim, and the proof is in the notes. But it would be a nice idea to try to establish this claim by yourself. It's just 2 lines, and then if it seems a little bit difficult, then you can look at the proof. And the claim is the following: max of x1 and x2, and note that this is no other than the infinity norm of the state x. If this is greater than or equal to max of 4u and 60u squared, then the term that we're denoting by g, okay, g of xu, is positive. Now this is norm of x. In fact, it's the infinity norm of our state, and this thing, this function is a function of norm of u, and that function is maximum of 2 class k functions, and the maximum of 2 class k functions is itself a class k function. It's not difficult to see. Therefore, we can call that function rho. Okay, rho of s, therefore maximum 4s, maximum 4s and 16s squared. Okay, rho of norm of u. Okay, where rho of s is max 4s 16s squared, and that's a class k function. Okay. So once again, the proof of the claim is in the notes. You can check if you cannot establish it yourself, and basically we're done. What we have obtained is the following: v dot. Okay. First of all, v is sandwiched between 2 class, or the norm of the state passed through 2 class k infinity functions, and also v dot is less than or equal to some negative definite function, provided that norm of x is larger than norm of u passed through that class k function. Okay. Therefore, we can invoke the previous theorem to establish the result. Hence, we can write it. V dot x is less than or equal to minus w3 of x. Okay. Note that w3 of x is positive definite. Okay. So v dot x less than or equal to minus w3 of x whole norm of x greater than or equal to rho of norm of u. Okay, this is our condition. condition 2. Condition 1 was that the Lyapunov function can be the sandwich between norm of the state passed through class K infinity functions. And ISS of the system, input state stability of the system, therefore follows by condition 1, condition 2, and theorem that we just saw, theorem 4.19. Okay, that establishes the result. Now, we'll briefly talk about how ISS notion can be used to establish the asymptotic stability of the origin of systems in cascade form. Okay. So what we mean is the following. ISS plays an important role in the stability analysis of cascade systems. So what we mean by that is the following. Okay. Suppose that here you have a system x1 dot equals f1 t x1 and x2. Okay, and then, excuse me, this should be here. Okay, and suppose that this system has the ISS property. Okay? This is the unwanted input that represents disturbance. And then the input or the disturbance of this system, which is ISS, is coming from another system. x2 dot equals f2 t x2. Okay. Therefore, this system depends only on x2, the evolution of this system. And evolution of this system depends on x1 and u is disturbance is coming from this system, and u is x2. Therefore, this system depends on both x1 and x2. Therefore, this whole thing we can consider as one big large system with state x1 and x2, and we can forget about u. Okay. And suppose that this second subsystem is, the origin of the second subsystem is globally uniformly asymptotically stable. Okay, and let's call together this chunk as one big large system, which we denote by star. Then the origin of the overall system, which we denote by star, has to be globally uniformly asymptotically stable. Okay, it's a very pretty result, and we're going to now apply it to a simple example. But let's state before the result in a more formal way, for the sake of completeness. Okay. It's lemma 4.7 from the text. Consider the system x that equals f t of x, okay, a time varying system without any input, where x dot, okay, or x is composed of two separate states, x1 and x2. And the evolution of the first part satisfies f1 t x1 x2, and the evolution of second part satisfies f2 t x2. Okay, and together we're calling the whole thing as f of t of x, where x is x1 x2 concatenated to make a single vector. x1 is in R and 1, and x2 is in R and 2. If these conditions are satisfied, x1 dot equals f1 t x1 u is input to state stable, where the last argument is considered as input, and the origin of x2 dot equals f of tx2 is globally uniformly asymptotically stable. If those two conditions are simultaneously satisfied, then it must be that the origin of the overall system x equals f of tx must be globally uniformly asymptotically stable. And the origin of x equals f of tx is globally uniformly asymptotically stable. Okay, now let's apply this theorem on a simple example. It's from the text 456. Show that the origin is globally asymptotically stable for the system x1 dot equals minus x1 cubed plus x2 and x2 dot equals minus x2 cubed. Okay. Now that we're using the term GAS instead of GUS because this system is time invariant, and for time invariant systems, global asymptotic stability and global uniform asymptotic stability are equivalent. So here is the solution. We're going to use level 4.7, therefore we're going to consider x2 as the unmounted input for the first subsystem. Okay? And if we can show that the first subsystem with x2 taken as the disturbance taken as the input, if it's the first subsystem is ISS and if the second subsystem is, the origin of the second subsystem is globally asymptotically stable, then the overall system by the previous result would have an origin that's globally asymptotically stable. Okay? So therefore, the proof contains two parts. The first part is we show that this is ISS. The second part is we show that that's globally asymptotically stable. How we can show that this is ISS? Well, we can use the theorem, the Lyapunov characterization of input state stability with which we began in our lecture. Okay, first, consider x1 dot equals f1 of x1 u, defined as minus x1 cubed plus u, where we're treating x2 as the input. Now we would attempt to show that this is ISS, and we're going to do that through the Lyapunov characterization of ISS. For that, we need a Lyapunov function candidate, and since this system is first order, the candidate almost always works the simplest candidate, which is 1/2 x1 squared. Okay, so take v1 of x1 as 1/2 x1 squared. Okay, and let's compute its time derivative. v1 dot equals x1 dot, because v1 is 1/2 x1 squared, and x1 dot is here minus x1 cubed plus u. Okay, so that is minus x1 to the 4 plus x1 u, and that we can write as 1/2 x1 to the 4th minus 1/2 x1 to the 4 minus 2x1 u. Okay. This 1/2 together, they make this whole one. And then this term times minus 1/2 gives us x1 u. So we just rewrote this part. And you will recognize that the first piece will become our W3 in our order notation. And this will be our G. And then what we will try to show is that this G, okay, this G without the minus sign, is positive, provided that normal of x is larger than normal of u passed through some class K function. Okay. So note that we can write x1 larger than or equal to q root of 2, and then you take the cube root of the norm of u. If this condition is satisfied, then x1 to the 4 minus 2x1 u is positive. Okay. Once again, if norm of x is larger than this constant times norm of u raised to the power 1/3, then this term is positive. Okay. Therefore, this whole term is negative, and that means we can write v1 dot less than or equal to this guy only, provided that this term is satisfied, and that gives us ISS. Therefore, x1 dot equals f1 of x1 u is ISS in state stable, because we can write v1 dot less than or equal to minus 1/2 x1 to the 4. So this is our w minus w3, this term. It's clearly negative definite for norm of x1 greater than or equal to 2 1/3 and u 1/3, and this we let our class K function, okay, rho of norm of u. Okay, so this is by the first theorem we considered in this lecture. The first system is ISS. So that was the first piece, the first part of our proof. In the second part, we have to show, if we can, that the second subsystem, which is autonomous, is the origin of the second subsystem is globally asymptotically stable. And then we can glue the two pieces together. The first subsystem is ISS, the second subsystem is such that its origin is globally asymptotically stable, and the overall system must be such that the origin is globally asymptotically stable. Okay, part 2. Now consider x2 dot equals minus x2 cubed. And we will establish asymptotic stability again by a Lyapunov function with v2 of x2, which is again of the same form, 1/2 x2 squared. Then v dot yields, okay, x2 dot is minus x2 cubed, therefore v dot is, or V2 dot is minus x2 raised to the power 4. Minus x2 raised to the power 4. Clearly, this is negative definite. Therefore, we have that the origin of x2 subsystem is globally asymptotically stable. Okay. Then here we have the first block, we have the second block, and by the previous lemma, those two blocks together imply the global asymptotic stability of the origin of the original system. Hence, by the previous lemma, so the overall system, the origin of the cascade system, x1 dot equals minus x1 cubed plus x2 and x2 dot equals minus x2 cubed has to be globally asymptotically stable. Okay, that's the end of our very straightforward and simple proof.